fancy name up there. Binomial radical expressions. Okay. Well, bi means 2, so we're going to have a couple of radical expressions that we're looking at. And what we want to do is learn how to add and subtract radical expressions, which usually you say, why don't we start with that? I mean, if you're in elementary school and they're teaching you math, you do add, then subtract, then you do multiply, then you do divide. That makes sense. But with radicals, just like as in powers, it's much easier to multiply than it is to add. So what we have to do here is start thinking, how is all of this going to work together? So, like radicals. We've heard that before. I mean, in algebra, we always talk about how algebra is a picky eater. You can't it's one of those little kids where my apples are touching my bananas, and they'll freak out and they'll not be able to eat it. Your A's are over here, your B's are over here, your C's are over here, and you can't mix those things together. It's the same thing when we talk about radicals. They have to be like radicals if you're going to add and subtract these. So radical expressions that have both, two things we have to watch for. The same index, the little number in the V, and they have to have the same radicand, the stuff under there. So when we look at these, there's two places we have to look. The index in the V, and right here underneath that. You couldn't find it in your big packet of stuff? Alrighty. The properties of algebra tell us that we can only add like terms. Like I said, A for apple only gets added to other apples. B for banana only gets added to other bananas. That's just how it has to work. Essential understanding for today. You can combine like radicals using properties of real numbers. So, if we see like radicals, how are we going to know they're like? They have the exact same index and radicand, the number that's underneath. And then we just think, okay, this is like a label. Square root of 2 plus 3 square roots of 2. Well, if I had 3 and I added another one, now I have 4 of them. And that's what you have. 1 square root of 2 plus 3 square roots of 2 is 4 square roots of 2. Makes perfect sense. Cubed root of 7 minus 5 cubed roots of 7. I had 1, but I had to subtract 5 of them. That would give me a negative 4. Negative 4 of what? Cubed roots of 7. Now they can get kind of messy looking, like these over here. Square root of 5xy, 8 square roots of 5xy. They're like radicals. I had 1, I added 8, now I have 9. Cubed root of 9x squared y minus 8 cubed roots of 9x squared y. Well, 1 minus 8 is negative 7, so now I have negative 7 of them. And the them is the radical. But in order to do that, we have to check to see, is the index exactly the same? Is the radicand exactly the same? Then it's pretty basic. So, combining radical expressions, sums and differences. How do we do this with addition and subtraction? If we want to add them, we check to see that the radicals are exactly the same, and then all we do is add the two numbers that are in front of them. They're coefficients. If we want to subtract them, we double check. Is the index the same? Is the radicand the same? And then we just do the subtraction with the coefficients in front. So really, it's easiest to just think of all of that radical stuff as a label. You know, this is how many of these I have. Down here, combining radical expressions, different from adding them. The sum of any two real numbers will always be a real number. But adding the square root of 2 and the square root of 3, well, we can't do that. They're both square roots, but one's a 2 and one's a 3. So you can't say, oh, that's square root of 5. That's what that is. No, it's not. They have to stay separate. The square root of 2 plus the square root of 3 is the square root of 2 plus the square root of 3. Unless we grab a calculator, we're not going to get any better than that. That's it. We cannot combine those two. And let me show you why. So this we already know is not true. Don't even write that one down. So if we punch in the square root of 2 plus the square root of 3, we get 3.146 blah, blah, blah. And the square root of 5 is not 3.146 blah, blah, blah. They're not the same. So adding and subtracting, much different than multiplying. The index and the radicand has to be the same. And this is exactly what you see up here as well for the Google Meet folks. Square root of 2 is about 1.414. Square root of 3 is about 1.732. And if we add those together, 3.146, not 2.236067977. It's not the same thing. So we add and subtract like radicals. Problem 1. So we're already supposed to know how to do this. What is the simplified form of each expression? Well, first we check and see if we can do it. Square root of 5x, square root of 5x. We can do this one. I have 3 of them and I subtract 2 of them. How many do I have? 1. And then we just drop the 1 because we don't need it. You know, if we have the square root of 5x there, everybody knows, hey, that's one of them. We have 1. So you just have to check and make sure you can do it. B, 6x squared square roots of 7 plus 4x square roots of 5. Can we do that one? Nope. Cannot be combined. They're both square roots, but the 7 is the radicand in the first one, and the 5 is the radicand in the second one, and we just saw you can't do that. This one looks fancy. 12 cubed roots of 7xy minus 8 fifth roots of 7xy. Can we do that one? Well, why not? Yes. So different reason, but same answer. Cannot be combined. Right there and right there. The index has to be exactly the same. So there were 3 of them there, and 2 out of the 3 we couldn't do. What is the simplified form of each expression? 7 cubed roots of 5 minus 4 square roots of 5. Pretty obvious when you read it off, right? Yeah, that one's I can't do it. One's a cube root, one's a square root. No can do. B says 3x square roots of xy plus 4x square roots of xy. Can we do that one? Yes, index and radicand are the same. So again, think of it as a label. What would go in front of the label for this one? 7x. Yeah, 3x plus 4x is 7x. 7x square roots of xy. C says 17 fifth roots of 3x squared minus 15 fifth roots of 3x squared. Can we do that one? We can. Okay, so that's going to be something fifth roots of 3x squared. What should go in front of that? Yeah. So the hardest thing we have to do here is double checking. Is the index the same? Is the radicand the same? And then we can put those together. We can combine like terms. But we have a little word problem. First day back, and already a word problem, right? Using radical expressions. In the stained glass window design, the side of each small square is 5 inches. Ooh, that's important. 5, 5, 5, 5. Okay. Find the perimeter of the window to the nearest tenth of an inch. Oh, 5, 10, 15. Wait a second. That's not 5. The sides are 5. But each one of these pieces on the edge comes from the diagonal. So let's see. Half of that little square would make it a triangle. You know what? This would be a special triangle. Because if this is a square, this would be a 45, 45, 90 triangle. And this will go a lot faster if somebody remembers from geometry how the side lengths are related in a 45, 45, 90 triangle. We can use the Pythagorean theorem. Anybody remember another way? Well, then we're going to do the Pythagorean theorem. 5 squared plus 5 squared equals c squared. Okay, well 5 squared is 25. 25 plus 25 is 50. How do we undo squaring something? Square root. Now, if we want this to be beautiful and perfect, we'd think, do we have any perfect squares that divide into 50 nicely? If so, what would we use? 25 and 2, we sure would. Square root of 25 is 5. So the Pythagorean theorem. Now, that is absolutely the way to go if you've forgotten the relationship of a 45, 45, 90 triangle. There is a song that helps you remember. And if you had remembered that song, then you could go, boom, it's 5 squared, it's a 2 seater home. I know what that is. Because it's 45, 45, 90. These are easy to name. For it's 1, 1, square root of 2 in a triangle game. I don't think we have any singers left in our geometry teachers anymore. Anybody have a geometry teacher that was doing singing last year with formulas and stuff? Freshman sang it? Okay. Because if you know the 45, 45, 90s, then you'd say, hey, I can take any side length and just take it times the square root of 2. And we wouldn't have had to do the Pythagorean theorem. But this works well. I mean, if it's what you remember, that's what we do. So, now what are we supposed to do with this? Well, each one of these is 5 square roots of 2. Now, I know what they wanted us to do. They wanted us to add all those together, but I really don't want to write them all down. Instead, I'd say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. And then I'd remember, real numbers can be multiplied by other real numbers. Radicals get multiplied by radicals. So I can multiply the 10 times the 5. And I'd get 50 square roots of 2, and this would be inches. There it is. You know, I keep thinking they probably wouldn't need to know the perimeter. I mean, what's going to happen if they want to really install this is they're going to want to know what, the length and the width is in order to get it in there. But it fits what we're doing, and so that's why it's important. Now, here's the got it. Let's say the only thing that changes is each one of those little squares is now 6 inches. Without doing the Pythagorean theorem, can you tell me what that new length would be for each one of those diagonals? 6 square roots of 2. Yep, and we had 10 of them. So for part A, what would our new answer be? 60 square roots of 2 inches. And B points out that there's 2 ways to do it. So if we remember 1, 1 square root of 2 as the relationship in a 45, 45, 90, then we can get this super quick. But we can always use the Pythagorean theorem too. That's one of those things. You want to know how to do it both ways. just in case on the ACTs you see something and you're like, I know there was something special about this, but I just can't remember it. Well, then use the Pythagorean theorem. It's your backup plan. Now here's what we already know. Before adding or subtracting radicals, you should simplify each of the terms. We ran into this before. They gave us things that weren't simplified, and then of course it took us a lot longer to get the answer if we didn't notice that. Oh, I suppose I should write this down so everybody will have this in their notes. My blue marker. There it goes. It's got some issues. So two ways. 45, 45, 90. 1, 1, square root of 2 times whatever you have for side length, or a squared plus b squared equals c squared. I don't think it likes that I covered up the green, but green didn't show up for your Google Meet, so I was covered that up. So before we try and add and subtract the radicals, we have to simplify those. Problem 3. That's all we get? And then they expect us to be able to do it. Yeah, because we've been simplifying radicals already. This is just using some of the things we already know how to do. So what is the simplest form of the expression, the square root of 12 plus the square root of 75 minus the square root of 3? Theorem cannot be combined. Oh, wait. We haven't simplified this yet. We know the square root of 12 is not in simplest form, because give me the perfect square we know goes into 12. Yeah. Square root of 75, that's not simplified. Give me the perfect square we know goes into that one. 25. And then you think about the square root of 3. Well, that one's done. You know, there's nothing we can do with the square root of 3. But now, all of those nice numbers that were on our power chart become constants out in front, called coefficients. So 2 square roots of 3 plus 5 square roots of 3 minus the square root of 3, we know it's going to be something square roots of 3. What's the something? Yep, 6 of them. 2 plus 5 is 7, minus 1 is 6. So sometimes we have to do a little legwork beforehand and get these simplified, and then we can add them and subtract them. Simplest form of the expression, cubed root of 250 plus cubed root of 54 minus cubed root of 16. Can't combine them as they are. Cubed root of 125, or, oh no, I just gave the answer away. I hate it when I do that. I was just going to ask. There is a perfect cube that goes into 250, which I bet you guys know by now. Well, now I told you what it was. So now here's what I know. Because I've simplified this one, I know these have to be something with cubed root of 2, or we're not going to be able to combine these. So we can kind of do an educated cheat and say, so does 2 go into 54? Oh, 27 times. 2 goes into 16. How many times? There's another one we should know. So what's the cubed root of 125? 5. Cubed root of 27? 3. Oops, I gotta remember to write cubed root. Cubed root of 8? 2. So now we can see they are like radicals, and it's going to be something cubed root of 2. So take a second here. What's the something? 6. 5 plus 3 is 8. 8 minus 2. 6 cubed roots of 2. So we have to simplify first before we throw up our hands and say, it can't be combined. I can't do this one. Our objective today was to figure out how to add and subtract We just found out they have to be like radicals, and if they're like radicals, well, then we can make it happen. And sometimes if they're not, we can simplify them and get them to be like radicals, and then go from there. So that is what we needed to get through today. So 6-3 day 1, page 378, 10 to 15, 17 to 22, 74 to 81. And then, like I said, for those of you in the classroom, I'm going to go ahead and get you a book, and anything else that you may need, although that packet full of stuff is pretty much everything. And John, you could have done that at home. Stay off that phone.